This video is about this video is about chapter 4, section 1.2. Chapter 4 is all about forces and Newton's law. Okay, so we're going to start talking about Newton's law, and we're going to see that all of the equations of motion that we've talked about so far are really just a part of Newton's laws. Okay. And everything that we've done so far can be related back to those equations of motion, the five kinematic equations. They're all related, and you can derive them from Newton's law. And so we're going to look at how to do that. Okay. I have posted these videos on Canvas. I think they're really great videos. I realize that the book actually has some great videos of experiments that are probably better than the videos that I can make here. For example, the two objects falling at the same time. I was struggling to do that with Pikachu and Charmander. I mean, of course, I love these two Pokemon, but they're just not quite as good as the publisher and Pearson. So I will be mixing in some videos from the publisher because I think they have good videos. If there's an experiment that is really well done, then I'm going to put that on the website so you can watch it because I can't do the experiments as well as they can. I mean, I totally could if I had enough time and money. I would actually love to make videos like that, but they're pretty good. So watch the videos from the textbook. I'll add some more, but I'm going to keep going through the stuff too. Since this is a shorter format course, I realize that I am probably talking too much. I think that the videos are probably too long. I mean, maybe they're entertaining, I don't know, but you have a limited amount of time and you probably can't listen to me talk for 5 hours. So, I'm gonna focus. I'm gonna only say the important things. I'm making that commitment to you and to myself because I just can't. If I talk too much, I can't make them fast enough. So, all right, here we go. We're gonna move a little quicker. I'm still gonna explain things, but I'm only gonna say the important thing. No tangents, or okay, maybe fewer tangents. The tangents are good sometimes. Like I feel like the stories are important. All right, chapter 2. Establish the connection between force and motion. Big takeaway here. Okay, nothing is gonna start moving unless a force acted on it, right? If an object is at rest, okay, it's not going to suddenly start moving. Okay, let's take Charmander here. Okay, this Pokemon is sleeping, and he will not move until an outside force acts on him. Okay, so if there is motion, there's force. All right, that's the connection. If something starts to move, then a force was acting on it. Okay, big connection. All right. Uh, A force is either a push or a pull force. We can pull on something. Maybe your kid is on a wagon, or maybe you're pushing a car, okay? But there is a person doing the pushing that's acting on another object. That object pushes back on you, okay? If you push on something, the object pushes back on you with an equal and opposite force. Okay, so we're going to learn how to identify all the forces. That's, I think, a big problem is uh, just identifying what force are in this problem. Right. Forces cause object to accelerate. And if we think about the Winter Olympics, okay, uh, without physics and Newtonian mechanics, there would be no Olympics. There would be no sports, okay? Because basically physics equals fun, okay? Forces cause object to accelerate. A forward acceleration of a sled requires a forward force. Also, the guys are running. They're applying a force to the sled to get it to go. Okay. And friction is pushing back on the sled. Wind resistance is pushing back on the sled. All of these forces are acting on the sled. And in the Olympics, okay, or even in NASCAR racing, that tiny amount of drag can make a difference. I mean, in the Olympics, we're talking about a thousandth of a second. In that instance, drag is absolutely critical. Okay. So in these high performance sports, you have to consider all of those forces. If you've seen the movie F1 with Brad Pitt, okay, there was a whole thing about designing it, how aerodynamic the car was, and they changed the design and it cut down the drag a little bit. And this was a big deal because I could give you like a winning edge. Just tiny little changes. Okay. Chapter 4 preview looking ahead. Hammer exerts a downward force on the nail. Surprisingly, the nail exerts an equal force on the hammer. That's true. I was at the Royal Rumble a couple years ago with my son, and I saw Kevin Owens jump off of a ladder and land on Cody Rhodes. He was laying on a metal ladder. And you know what? I think I'm gonna play that video because I took a video of it and it was so horrific. I'm gonna take a video and then I'm gonna show you and we're gonna talk about. Let's watch this educational video. Okay, well, as you can see from the video, yes, Speed hit Logan Paul with some considerable force, I would say. It looks as though he is. I think it maybe looks worse than it actually is. I would say from this video, um, well, speed center of mass is about 1.5 meters above Logan Paul. Okay, so and it looks like yeah. So, but the thing to remember is that, yes, speed is going to exert a considerable amount of force on Logan Paul, but Logan Paul will also exert the same amount of force on IShowSpeed. So that part is real. I think stunts like this can actually break bones. Um, of course, is wrestling fixed? Probably, but these stunts are real, and so even if you don't really care about whether the outcome is fixed, I mean, they put on quite a good show. And falling 1.5 meters and landing on someone else, that is very real and can probably break some ribs. All right. Just like when I Show Speed hits Logan Paul, the nail applies an equal amount of force to the hammer. That's why we don't hit nails with our fists, obviously, because the nail would push back on your fist, probably break your bones. But when we have a big hammer, right, then it's not going to hurt your hand. Okay. So that's action reaction pairs in the book. Those basically when one object exerts a force on another object, that object exerts a force back. Okay. Uh we already saw, and I made a video of this about the acceleration an object experiences when it changes directions. Okay, there's an acceleration vector, and if something's moving in a straight line, it is not going to change directions unless a force acts on it. So there's some kind of acceleration happening. A force is pushing that object. Okay, something makes it turn. If it slows down, a force is slowing it down, or if it speeds up, there's a force acting on it. Okay. Rocket ships. There is a huge force coming out of the back in the form of jet fuel. When it burns like that, it shoots the particles out with a tremendous amount of force, but they push back on the rocket with the same amount of force, which is what causes the rocket to lift into space. All right. A swan is landing on an icy lake. And she is sliding across the lake and gradually comes to a stop. As the swan slides, the direction of acceleration is okay. Well, she's moving to the left on my screen. Okay, and so she comes to a stop. That means that the acceleration had to be pushing back the other way. So acceleration was pushing against her motion to get her to stop. So it's to the right. All right, reading questions. Hopefully you read the book. Okay. Yes. So here are Newton's three laws. Let's go through these real quick and then I'm going to talk about them. Okay, the first law, a body at motion remains at motion unless something acts on it, or if it's in motion, it continues on unless a force acts on it. Okay, that's pretty simple. Okay, Newton's second law, force equals mass times acceleration, right? This is a huge equation. Write this on your card, for goodness sakes, write it right now. F equals ma. Uh, if you don't remember anything else from this, please remember that equation. Force equals mass times acceleration. Okay. And we're going to talk about that a lot. But every action there's an equal and opposite reaction. Okay. So I want you to play this game. Okay, find somebody where you are. Okay. And basically I want you to stand about maybe half a meter away or maybe 12 inches away from that person, and you put your palms up like this, okay? And you push against each other, and you can't take a step, right? You can't take a step, and so, uh, and then you try and knock the other person over, basically. Go find somebody and play that with them, okay? You need to go do this experiment right now. Get up, go outside. I need you to go do it. I'm actually going to play it with my son and make a video. My son, I think he's taller than me. He says he's stronger than me. He probably is. If he's not now, then he will be in like 2 months because he's growing like crazy. All right, go play this game and then come back and watch the rest of the video.
3 out of 5? 3 out of 5?
No, whoever gets the 31st wins.
Okay. Yeah, that's best. 3 out of 5.
Dude.
Whoa, whoa. See. Oh, oh, oh. Oh, hey, yeah, no, no.
All right. So as you can see in the video, um, I have a much higher mass than my son, and so when he pushes on me with a little bit of force, actually, I push back on him. I don't even have to do that much. Um, and so whatever force he exerts on me, I exert back on him just as a consequence of Newton's law. And so, since I have much more mass, when he pushes on me, he's really pushing himself away. So, if you've ever played this game with somebody, it's a good example of Newton's law in motion. And I think uh, that's why we're going to be, vectors have been so important because now that we're at the place where we're talking about forces, it's going to be really important to understand the direction of those forces. Okay, so for example, let's take my hand here. Okay, when I close my hand, right, think about all of the different muscles in your hand. Okay, when I have a bottle here, I'm picking up this bottle, and right when I grasp the bottle, okay, think about how many different forces are in your hand. Okay, there's force vectors going everywhere inside of your hand. There's a force here at each of your knuckles. Those muscles are applying force in a certain direction. Okay, and that results in a force on your hand here with force vectors pointing inwards and on each side, which is what keeps the bottle in your hand. Okay. So, and if you think about all of the muscles in your hand, okay, there are hundreds of muscles that allow you to pick things up. And each one of those muscles in your hand applies a force vector in a certain direction. Okay. So the human body is really amazing because um, the physics just in your hand alone are pretty crazy. But we're going to talk about forces, and then I'm also going to do some problems, lots and lots of problems. All right. Thanks for watching this video.